What does it take to do the most important job in the world? More than 100 years ago, a young farmer in rural Germany spent much of his time fixing a notoriously unreliable hay binder in order to get the job done. So, he went on to invent a better tool. After starting his company in 1913, August Claas began a long line of innovations designed to simplify the lives of countless farmers around the world. Today, the company proudly supports over 11,000 employees, 5,000 patents, and 500 different products sold in more than 160 countries through 35 production and sales facilities and hundreds of importers and dealerships. Our customers, independent, business-minded ag professionals, pay attention to the little things because they know they make a big difference. Bright minds who demand more from themselves, the land they live on, and their equipment. We're here to build them brighter tools to help them achieve their goals. Tools like our global industry-leading Jaguar forage harvesters, outstanding hay and forage tools, top-performing tractors, and the unequaled Lexion Combine. Equipment designed to save time, increase productivity, improve profitability, all while providing our customers with greater insight to make brighter business decisions. And make the most important job in the world just a little easier.
Thank you for considering to work with Claas Omaha for your senior capstone engineering design project. I'm Matthew Cook. I'm the Director of Manufacturing for Claas Omaha. And behind me is arguably one of the most complex machines in the world. This particular one is made in Omaha, Nebraska. Today, a modern combine harvester utilizes various functionalities to efficiently harvest the grains needed to feed a growing population. In the last 20 to 30 years, the complexity of these machines has increased significantly. From high horsepower engines to the drives to threshing, separation, a multitude of other functionalities that allow a farmer to efficiently harvest. That combined with new technologies, GPS, auto steering, data acquisition systems, these are all combined to make the farmer's job easier. But one thing hasn't changed in the last 20 years. It's the number of bolted joints used to make machinery such as what you see here in front of you. Here you see examples of where our technicians have marked manually the bolted joints when they've reached torque with the specified tool that they've used. And what we would propose is that we develop a system, an add-on to our torque tools, that would systematically, mechanically provide a witness mark upon the tool's completion of its torque cycle. This is an example of one of the air-powered tools that we use on every single bolted joint on this machine. Whether it be a manual click tool, an air-powered tool like this that costs maybe $3,500, has an accuracy of about 5%, to DC-powered tools, every single bolted joint on this machine is torqued to specification. What we would propose is an add-on solution to this tool that takes the signal from the clutch, the vibration occurring as the torque tool reaches the set torque limit, or the air exhaust coming out the back end that occurs at the same moment. Take that signal, process it, and provide a means to provide this witness mark to the bolt head. The proposal that we're providing you today would not only benefit the production of this Lexion Combine in Omaha, Nebraska, but it would as well be useful for the other various products and facilities Claas has worldwide. It's very apparent that the quality control that we're pursuing with this idea isn't applicable only to Claas, but instead to our competitors, as well as a wider range of industries making very complex machineries with a very complicated arrangement of bolted joints. We hope you choose to partner with Claas to address this very important topic. And now I turn it over to Chase Goddard, our manufacturing engineer for Claas Omaha, to discuss more of the purpose and the context behind this proposal.
Thanks, Matt. We'll head out to the production floor and look at these pneumatic tools in operation.
Go.
All right, here we are on the shop floor. Assembly technician Dennis, he's going to demonstrate this fastening joint here. Go ahead, Dennis. So he'll go through, tighten all these bolts down within an assembly, and then once he's done, he visually marks them. Here, this has already been done with blue paint. Those have reached the desired torque values.
Got more of the other. Over yon.
And then he'll go through and mark with a paint pen to show that his torque has been achieved, so it can visually be inspected by quality. Alright, so here's another example of maybe a tight fitting area where an air-powered tool would be needed. Again, tight fitting area needs to have minimal interference with the machine, and we mark with the paint pen to visually see again afterwards. All right, here we have an example of a little bit larger air-powered gun, 207 Newton meters. So here we go. All right, now that we've seen some shop floor examples, I'm going to give you guys a little update on the bolted joint witness mark project proposal for the 25-26 school year. Here we can see the existing technologies. Onichi makes a marking tool with manual torque wrench. We're of course looking to develop a add-on torque tool or add-on marking tool to a air-powered tool. So scope of the project, we're looking for an add-on device to existing tools, and currently what's been done in the past 2 years. The first year we really provided this proof of concept. Second year, we had further development, industrialization, more robustness. Now we're looking for a little bit more miniaturization It's still quite big and bulky. But a little bit about the tool is we use an accelerometer and the data from that accelerometer to determine when we should fire a witness mark next to the bolt head. So some of our constraints and considerations is that, of course, we have to have a low profile. We have tight working spaces, quick drying and permanent. We're using Dykem, and we also have to consider the functionality of the nozzle and minimize buildup. We have to have a reliable signal. Of course, you don't want to be firing this paint mark when torque is not achieved. And then we have to have it be durable. We will use a battery power supply and the air pressure line from the shop floor. And then, of course, we have multiple size torque tools, different shapes, of course, the different sizes, and different socket head sizes as well. So we get this technology kind of dialed in, and we should be able to adapt to different sizes, tweak some codes, tweak a little bit of the routing, the hardware on the lines, should be manageable. Some of the technologies you guys will be using, we have, like I said, an accelerometer, some pneumatic controls, solenoid, paint and ink marking technology, a controller. Currently we have a developed PCB from last year's project team, power supply, probably utilize the onboard solution from last year as well. And then we have component design and machining. Of course, Klaas will assist with the budget, guidance, and providing access to machining technologies. Hopefully you consider our project for the witness mark, and looking forward to working with you guys. Thanks.